Okay. So it's pleasure to have last speaker of this semester, Yi-Shuai Niu, who is going to talk about difference of sums of squares decompositions for polynomials. Go ahead.
Okay, thank you so much. Thank you for the kind invitation. As you know, this is the last lecture of the, not lecture, member seminar for this semester. So I hope you enjoy it. So a brief introduction about me. So I'm Yi-Shuai Niu, currently an associate professor at BIMSA. And my research interest is focused on optimization theory and algorithm, machine learning, and high performance computing. So today I will bring you one of the most famous, my favorite topic in recent years about difference of sum of square decomposition for polynomials. So you may know here about the sum of square decomposition for polynomials. So that's something very well known, some topics and highly related to the Hilbert's 17th problem. And that is exactly the story, the starting of the story. And today, what I will talk about is the difference of the sum of square. So it's some extensions of sum square decomposition, and which is primarily based on what we have produced in a recent paper published on SIAM Journal Optimization. Okay, so of course I will not involve any details about the proof or something like that. Just give you a brief view about what we are interested in and what is the related history, and maybe you are interested. Okay, so the first I will present about the problem and the motivation, what we are going to do. And then I will start from the history of sum square decomposition until now, and what we are focused on and what we have found. Okay, and after that, I will just give you a brief view about some different sum of square decomposition techniques and the different convex sum square decomposition techniques that we explored in a recent paper. And at last, I present some 3 open questions that I hope that you will enjoy it. Okay. So first, about the problem. So what we are going to do is once you give any kind of multivariate real polynomial of any degree, okay, we want to find a particular decomposition that is the difference of sum of squares, or even particularly if these sum squares are convex, that's called difference of convex sum squares. So the question is that, can we indeed do it, and how to do it, right? And so formally we can define the DSS and DCSS just as in its name. It's if there exists some sum square or convex sum square such that any polynomial t can be written as S1 minus 2. So S1 and S2 are sum squares, okay, or convex sum square. And so the research, the extensive study about this problem is given in this paper. So why we do it? Okay, why we study such kind of problem? So firstly, of course there are many theoretical value and practical value, and here I give several of them. First, it helps us to theoretically, it helps us to have a deeper understanding about the inherent fundamental structure of polynomials. Okay, we can come back to the history of Hilbert's 17th problem. So initially, a question, a very interesting question is asked that, is every non-negative polynomial a sum of squares? Okay, as a polynomial non-negative, maybe it can be expressed as sum of square. And the problem is answered by the David Hilbert in 1888, that just a few of polynomials, there are some conditions that I will just show you later, can be equivalent between SOS and non-negative polynomials, but most of them are not the case. Okay, so that is a initial problem. Then David Hilbert extends this question to the famous Hilbert 17th problem. The question is that, can any non-negative polynomial be presented as a sum of square of rational functions? Means that is a rational function, and above and below are both sum of squares, something like that. And of course, this fortunately, the answer of this question is yes, and it's first proved by Emil Artin, okay, in 1927. But Artin's proof is not the end of the story. Okay, give a good answer, and of course, found the real algebraic field. And after that, it's just you can consider the starting of the new chapter in mathematics, and a lot of related fields, a kind of real algebraic geometry, theorem, positive polynomials, and the one that I'm most interested in, optimization involving polynomials. So all based on this breakthrough. Okay. So recently we are very interested in that is a particular decomposition, as I have just talked about in the title, difference of sum square, okay, or difference of convex sum square. And the answer is fortunately yes, and it's provided by us. They provide a further step towards a deeper understanding of the polynomial structure. Okay. So the second theoretical value is about the optimization theory. So an interesting question about the sum square decomposition is that if you want to check a polynomial sum square, it can be formulated as a particular structured convex optimization problem. It's called the semi-definite program, formally defined in this way. Okay, and if the problem has a solution, then the polynomial can be presented as sum square. So this is the fundamental result. And in our work, we can extend the result to DS and DCSS, meaning that we can also check a polynomial can be right under DSS or DCSS if a corresponding SDP is solvable. Okay, has a solution. That's the important thing to make connection between the optimization and the polynomial decomposition. The second is, of course, our initial motivation. That is, once you have any polynomial optimization problem, can we find some more efficient method, okay, to solving this kind of problem? You have a lot of applications like that, and the classical method perform very inefficiently. And the answer is that we can, if we can write as sum square, different sum square, or different convex sum square, we can employ a difference of convex programming technique that is very efficient in large-scale optimization problem. Okay, and so we can make connection of them to get a better numerical performance.
Can I ask you a question?
Yeah.
So the problem that Hilbert negatively answered, positive coefficients, right? That one.
Okay.
So what was the condition? Non-negative.
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 Yeah.
Coefficients.
Non-negative.
Yes. So here, for the one you can prove, can be negative one.
Yeah, there's any polynomial. It can be both positive or negative. That's why it's an extension of that. So you can think about for any function, either positive or negative, you can write as a difference of two non-negative functions, right? As a positive part minus negative part. But you may destroy the differentiability. But here in polynomial, you can write both of them as sum squares. And so this is the very interesting and particular feature, right? So, so just a brief view about what is the polynomial optimization is interested in solving minimizing a polynomial function f. So it's a real polynomial with a variable x in Rn. Okay, n various polynomial functions, and you can see that in fact it's equivalent to some kind of difference of convex optimization that's to minimize difference of two convex functions d and h are both convex functions and not obligated to be supposed to be non-differentiable. Okay, so it covers the field of polynomial differentiable. Here even it can cover a very more large set of problems, and you can show that in theory any polynomial optimization DC optimization because any C2 function is DC function. Okay, but the question, one open question, formally open question, is that how to formulate any polynomial SDC. But right now, it's no longer open question because we propose DS and DCS decomposition leading to DC decomposition for polynomials of any degree. Okay, so that is the important value. So here just a very short example to show that what's going on. For example, if we have a trivial of quadratic form fx, written like this, Q is n times n real symmetric matrix, and there are several kind of classical DC difference convex decomposition for F. Some kind of function like G part is a quadratic function, and H part is just is also a quadratic function in this case. Okay, it's sufficient to find a large enough parameter mu to ensure both of them are common. Okay, and another is that you just take H as G, okay, and you can do the similar thing. Okay, but here, summa square, that is another famous decomposition we call the spectral DC decomposition. That's based on the spectral decomposition of a matrix Q. Okay, it's a symmetric quadratic, symmetric n times n real matrix. So we can find octagonal matrix P and the diagonal matrix lambda. So with all positive positive eigenvalues on lambda plus and negative eigenvalues on lambda minus. So the part G and the part H can be defined like this. They are both summa square. Okay, so you see it's a difference of summa square because G minus H provide any quadratic form P. Okay. Any question here? Okay, I haven't given you detail, but I think it is clear enough, I hope. Right? So our work, in fact, is try to extend this kind of decomposition to any variate, any degree polynomials. Right? So that is the example. So we can see that's the reason why this kind of technique is very useful, because once given such kind of decomposition plus a technical DC optimization, so many real-world problems can be solved in this technique. Okay, because they can be formulated as a polynomial optimization problem with polynomial equations or inequalities, minimizing or maximizing some polynomials like that. Okay, so for example, some data science, machine learning, matrix analysis, many of them. Okay, I have due to the time and framework, I will not give you details, but just trust me, there's a lot of them. Some of them we have started, some of them say maybe you can study in the future. That's a very interesting thing. And okay, so now let's talk about some SOS decompose, some history about polynomial decomposition based on summa squares. We had to use very common notations Rx and Rdx for the vector space of real valued polynomials with variable x, and D meaning that the polynomial with degree up to D. Okay, so summa square is just some polynomials that can be rewritten as summa square of some other polynomials, and are highly related definition is Ph.D. or non-negative polynomials. That is P defined non-negatively over the whole field Rn, right? And the story just started in 1885. Once Minkowski, during his Ph.D. defense, he made a bold conjecture that SOS is different to SD, Ph.D., but haven't given any explicit example. And David Hilbert, just one of his examiners in the Ph.D. defense, and he believed what he proposed, but just after 3 years later, he proved in this paper, 1888, that this is true. Okay, every polynomial in n variable and degree b is summa square only if 3 cases. One is just n equal to 1 variable only, univariate case. The second is you can have degree equal to 2, have many variables, quadratic case. The other one is n equal to 2 and degree equal to 4, bivariate quadratic case. Okay, and meaning that in all other cases, there always exists some counterexample. Okay, that a non-linear polynomial cannot present it as something. So that is a famous result. Okay, but unfortunately, Hilbert haven't provided any explicit example. They just prove it in an unconstructed way, okay, to show that the result is true. And just after 70 years later, and it is the first counterexample provided by Morskin for other purpose and recognized by some people in the field of optimization, like Todd, and show that this polynomial, just with two variables, it is indeed a PSC, just as in this figure. Okay, it's always non-negative, and it cannot be rewritten as sum of squares. This is the first example. And after that, the series of examples, and in fact, infinite many examples exist as a counterexample. This is a typical one. Okay. And one of the important reason to study sum of squares is that for checking a PSC, the polynomial is non-negative definite, this is NP complex problem established in this year. Okay. But the sum square can be checked in polynomial time. Okay, because it's equivalent to SDP, and SDP is a convex optimization that can be solved to any desired position in polynomial time, right? So that is the important reason why many people interested in sum square. Right? So here we think about a little bit extension about sum square. Before, sum square may not be convex. If we add some convexity inside, that's attracting our attention in recent years, because convex is important in optimization. Optimization problem with convexity, everything is beautiful. Okay, otherwise it's extremely hard. So naive extension is that we just combine sum square with convex. That's called CSOS, that we defined in in our work, and we can show that the set of sets polynomial is a proper count. Okay, and so all properties of the count can be used in this field, and it helps us to establish the decomposition of sum square, difference of convex sum square. And another similar definition, but just similar in name, okay, it's quite different definition, is SOS convexity proposed in this year, okay, by Hilton and Ni. This is the kind of polynomial whose Hessian matrix can be written as another polynomial matrix M transpose M times M, okay? So it is this kind of matrix called SOS matrix. So both of them are convex, but the later one may not be even non-negative. Okay, so they are in fact the difference, and we have also shown that it cannot be written as a linear displacement of SOS convexity to CSS if it is defined as negative. Okay, so here is this graph shows the global relationship between these definitions. So what we propose is CSS, and you see that they have no inclusion. Okay, just the intersection of them provide the PSCSOS convex. That is a set we are interested in practice, because it can be verified in polynomial time. And you can also see that all these inclusions are strict. Okay, you cannot inverse the inclusion because all of them has counterexample. Okay, I will just skip the details about that. And the similar thing about complexity, you can see that convexity and CSOS in general, that is NP hard, but the others can be checked in polynomial time. So what we are interested in is that some polynomial are both CSS and SOS convex that can be checked in polynomial time and have very beautiful properties about non-negativity and so on. Right, that's something we are interested in. So in the last few minutes, I will show you some practical method, the major result and the practical method to construct such kind of decomposition. The major result consists of the representability and convexity. To answer the question, if any polynomial can be represented as this kind of decomposition, that is answered in this theory. Okay, but first we show that all of them, DS or DCSS, are in fact a vector subspace. So we have one inclusion, and other inclusion established here. In fact, any polynomial can be right-handed DS or DCSS, and the number of decomposition is infinite. It's depending on what basis you find. I will talk about this. And particularly, the degree of each component is not smaller than this one. This means that if degree of P is even degree, so it's just degree of P. Okay. Otherwise, the degree of P plus 1. Okay. And particularly, there exists the minimal degree decomposition. Okay, because the each component has the maximal degree equal to this one. Okay. In fact, the degree should be larger than this one, but here it has a maximum just equal to this. This is the optimal degree. That's something we prove in theory. And the complexity to constructing this kind of beautiful decomposition, that we can show that it can be, both of them can be constructed in polynomial time for any desired position in by solving some matrix. Just one IDP is enough. Okay. And here I just give you a quick review about some decomposition, practical decomposition technique without solving anything. Because solving a large scale ICP is expensive, despite in polynomial time. But in practice, it could be difficult. But here we propose some method. First is just extension of the spectral decomposition for quadratic form that we call the spectral SOS decomposition. The idea is similar. So given a basis B is a polynomial vector, we call it a valid basis. If it exists some matrix Q called a grid matrix, such that the polynomial P equal to this. Okay, this is true for every X, meaning that the coefficients for left side is equal to the coefficient on right side. Establish the equivalence. Okay, and once we get a spectral decomposition of the matrix P, and then a matrix Q, then the polynomial P can be just raised at different assumptions. It depending on lambda I, eigenvalue is positive and negative. Positive on the one side, negative one. Okay, so this gives you a trivial view why how to extend from quadratic to any degree polynomials, and why is defined like linear. Okay. So here, in practice, if you want to apply that, you should find a basis. Right. So there are a lot of ways to construct that kind of basis. One method is called the direct basis, meaning that we collect all the monomials and with one, if there is no constant part. Okay. And using this set, you can see that the corresponding decomposition whose maximum degree of the components is just twice of degree of the basis, and that is a degree of basis, degree of the polynomial. So it's a easy way to construct decomposition. But
你们有东西卖吗？还是我要自己买？有卖的。有什么样的？
And the second one, it's called minimal basis. That's why you want to find the optimal degree. So the reason, so it's just a need to find the basis, valid basis, like the degree for half of the degree of the polynomial. You can, for example, listing all monomials with degree.
一起买有折扣吗？
For example.
就是买3
And this kind of decomposition provide an optimal degree. And this is the second
这
technique.
个有别的样子的吗？
And
这有什么样子？
another type of method is called parity decomposition, meaning that for each monomial, x power alpha, we can factorize as a part O and times E.
这个谁非保守的？是你们守吗？还是别人守？
all variables
谁
are
非保守呢？
all degree, okay? And E square, of course, is the
那个是有后
degree.
台，
And
你也
if
不知道。
find the decomposition for OX, multiplying by square, we will have yes, right? And clearly here we have also provided two different kind of techniques. When the parameterized, just using a parameter any s no negative to get a trivial part O, and a similar improved using this kind of O, you can get a minimal degree. Okay, here we cannot minimal degree. Degree is the degree of m. And here I just to show you some experiments using different kind of practical math. If we here I have 1,750 polynomials random generated, different size of n, number of variables, the degree of the polynomial, and the range of the variables and polynomials covers almost all practical applications required in practice, polynomial in practice. And the density I also test from some sparse case to some dense case. So combine all of them, it gets this set of polynomial. And you can see that here is the comparison between different kind of practical method. And this is along the increase of size n, size z, and the density. Okay, so the vertical is a log time, computing time. So the last figure is about okay, the degree of each component, maximal degree. So it can be different depending on the tested cases, right? And in general, can just summarize that the minimal basis, the last method that I introduced in the last slide, that provide the best method and the decomposition with degree minimized degree, and the computing time is just this purple line. Okay, it's not the best time, but among the best time, the degree is minimized. So this this compromise, this should be the best method provided in practice. Okay, and here is just a part computing result. We use 60 processors, and you can find that this method improves the part decomposition monomer by monomer. You have a 4-fold maximal speed up, and it's around 15 processors. And if we use most processors, you cannot get the speed up. Okay, and not for the PP. PP we have no speed up. I think I have no more time, but I just to tell you that in difference of convex sum square, we have some similar techniques for parity techniques and improve the one to get the best degree or minimal degree based on this key identity. And based on that, we get an optimal degree decomposition. Some similar idea, but a little bit harder to get a result. And here is the third one. Is just recently we developing another paper, probably linear multilinear algebra, that is called power sum, meaning that we write the decomposition in form of the power of some linear form. Okay, some linear forms, and this is constructed based on this particular matrix we call power party matrix. Okay, here each alpha I is in this set, and this set is each element alpha I. It's all combinations, all possible choices to put in D balls into n bins. Okay, you get this matrix, and we can show that this matrix is always non-singular for n and d, and if n, the number of variables larger than degree. Okay, so in this case, the matrix is very sparse. With this sparsity, we can compute exactly the number of non-zero. And you can see that if for many degree d, so if the number of variables is around 13 or 15, you get 90, higher than 90% of the sparsity, meaning that the matrix whose inverse can be computed very effectively. And based on that, we can just the coefficient of this decomposition is just computed by solving this sparse linear system with Cosmos impact. Okay, and so this is for all for even degree, similar for all degree. So we just keep, and this is in practice. We can also have some homogenizing and dehomogenizing techniques, because any polynomial can be homogenized by introducing additional variable xn plus 1. And once you get this even degree polynomial decomposition, then you just set xn plus 1 equal to 1 to get the decomposition of the original one. Okay, that's the idea. And both of them can be proved to provide the best degree decomposition. And this is a similar comparison result. Just two important things. One is DSS is easier than DCS because adding convexity is more difficult in practice. Okay. The second is that among DCSS, this method, minimal degree 1, provides the best result. Okay. And here is the speed up. As well, we get some 18-fold speed up of 12-fold speed up for different kind of methods with some less than 60 processors. This is just a comparison between the power sum decomposition, two kind of power sum decomposition. So you see that it costs nothing for the TG is the time for generating the matrix. That is the most expensive part. Once the power product matrix generated, to finding the solution is just something, 1 second, 3 seconds, something like that. It's very cheap. Okay. And some open questions. The first is that we should find some establish the theory and the method for constructing some minimal degree decomposition with the minimal number of quarks. Because if the degree is minimized, the number of quarks should be exponential, for example. And how to make it shorter, because more terms to be optimized, so more computing time is may require. The second is that the power sum type decomposition, how to make as well a minimal number of quarks as well. The third is the undomination, because the DSS we have undomination, meaning that I haven't talked about this in the slide, but this is very important because undomination meaning that you get a better approximation for polynomial optimization problem. If you get a better approximation, so you need a less number of iterations to get convergence. So undomination is important. Okay, that's all for my talk. Many thanks for your attention.
Questions?
Yes, please.
What is the topological complexity of the DSOS or DCSOS algorithm?
How many?
The topological complexity.
Complexity.
Topological complexity.
Yeah. I have shown that in theorem, if you want to solve this, okay, should be here. Right? If in theory, if you construct a composition, it can be computing polynomial. Okay? Just because the corresponding SCP can be solved. That is the best complexity in theory. And in practice, so depending on the method. Some method, solving, for example, just a linear system in a sparse linear system, that can be doing right. So some algorithm it can be we haven't enough complexity result in practice.
I mean the topological complexity introduced by Stephen Smell. It is the number of branch nodes in the tree of the algorithm.
Really? Okay.
Number of branch nodes. Branch nodes.
Okay.
What is the topological complexity of this algorithm?
I'm not quite understand your question. But in SCP, that is a polynomial time.
Yeah. Okay, thank you.
Okay. Maybe we can discuss later after. Yeah.
More questions.
More questions.
So if the functions that we try to optimize have two or three, not just one polynomials, is it this decomposition also works?
Yeah, sure. This decomposition can be applied to any number of variables, any degree.
Okay.
Yeah. So two is just a trivial example to show what's going on, what is exactly competitive formulation. But it can be applied. And in fact, that is the reason why we started this problem. We want any degree and any firm. Yes.
Very powerful.
Thank you.
More questions?
Sorry, just to check something. So all these algorithms, they're suitable for those polynomials that can be decomposed, right? So
No, any polynomial can
No,
be
I mean-
decomposed. The in theory 3, the first line shows that any polynomial can be decomposed.
So, but I remember in the maybe I have maybe I think something wrong. Just I remember in the beginning you said that so the decomposition only happens with fractional functions, but not polynomials, right?
No,
So for
this is just for non-negative one.
no,
that's
okay,
not
Okay.
negative.
okay.
For non-negative,
Art's
Hilbert 17 for non-negative one.
Okay, so for if we have a negative here, then any polynomial can be decomposed.
Yes, here I started any polynomial, any
Oh.
row.
Okay, thanks.
Actually, let me ask you a question. I couldn't
Okay.
intuitively even figure out. So let's say, how did he prove that for perfect square even degrees, 4, 16, 9, or even 9? 9 is, I think, obvious because it's not positive definite.
Yeah.
But for perfect square even degrees,
Yeah.
how did he prove that there are counterexamples always other than n and d not equal to 2 and 4? What's the intuition behind?
Yeah, it's based on Cayley something theory. It's established by Hilbert. I think you can just check in this paper 88. It's providing unconflicted based on Cayley something theory. Yeah, because it's I haven't
Surprised.
because well known. I haven't viewed in detail. If you're interested, I can discuss it in details along.
And how can you tell me a little bit what's the intuition behind when it is semi-positive definite, then it's polynomial time to solve? What happens there?
Okay, so in fact, it's easy. Just here you see I write in some page. Yes, here. You see the px can be rewritten like this, right?
Okay.
But think about you have a full basis. It means that a list of all existing all monomials, okay, from 1 to the maximum degree, and you find any possible q, non-negative definite. If it's non-negative definite, by the eigenvalue decomposition can be written like this. So both sides, you see, if you write like this, it's just all of them are because all eigenvalues are non-negative, right? So it's just a sum of squares. So it provides the representability of SCP and equivalence with
I see.
sum of squares.
And then your result also, another result was that when the Hessian is, what is the property on the Hessian?
The Hessian is
It should be
here. Yeah. So using this definition as a matrix, it provides a possibility to check that polynomial is convex. Because you see the Hessian matrix is written as this one, is meaning that the matrix is non-negative semi-definite, right? So it's convex. It's a necessary condition for the a sufficient condition for convexing, right?
So maybe some naive again question, when you said open questions are to reduce the number of the perfect square terms and so on, does it have to do with some kind of a rotation of the coordinate frame to represent these m's in a different coordinate frame?
Maybe.
Is that how you do it? Like, how should I think about it?
Yeah, we are thinking about the cost. If you present some basis, means that we find some suitable basis such that the representation is as sparse as possible.
Yeah, exactly.
That's exactly what we are doing. Exactly what we are doing. Exactly.
Kind of
some rotation and then some turning just cancel out, and that's exactly what we are doing. But it's not trivial, you know. So if you for convexity, based on convexity, ensuring the subscript is convex and presenting a sparse space, that's a challenge. Yeah.
I see.
Yeah, really a good idea. That's intuitive that we are doing right now.
More questions?